modified the title of my talk a bit because besides the alloperoxidase stuff, I will today also show some new results that we obtained on titanium MCM41 oxidation catalysis. So the goal of this talk will be to try to convince you that single turnover monitoring by fluorescence spectroscopy can be a valuable tool that is complementary to the more traditional techniques. Can you understand? Okay, maybe this is better. So this morning we already heard a beautiful lecture by Professor Beckman, so I can keep the introduction of my talk quite short. So on this slide I kind of summarized some of the advantages of fluorescence spectroscopy. And in the two examples that I will give you today, we will kind of push this technique to its limits concerning the sensitivity. So we will try to monitor individual reaction events. We will try to see how individual molecules are formed by the catalyst. And in this, in particular, in the second example, I will also try to show you how we can push the spatial resolution of this technique to its limits. So in principle, optical techniques are limited by the laws of diffraction, meaning that we have a resolution for optical light of a few hundred nanometers. But there are tricks, and especially if you're looking at individual molecules, there are tricks to obtain a better accuracy and a better resolution, even in the nanometer regime. That I will show you in the second example. All this can be done with a fairly good time resolution. We can follow dynamics at the millisecond scale. And we can operate it under in situ and mild conditions, contrary to electron microscopy, for instance. Okay, so what is now the key to observe individual turnover events or individual reaction events? Well, there are a few approaches possible, but the most versatile is schematized in this slide. So what we normally do is we immobilize our catalyst in a very dilute way on a core slip, so that we can really look at individual catalysts, one catalyst at a time, and we apply a substrate or a reactant that is not fluorescent, but upon the catalytic action is converted into a very fluorescent product. And it's, this product should have properties, fluorescent properties that are so strong that we can detect the fluorescence from this single product molecule. So what you will detect then in a fluorescence microscope, if you look at the intensity originating from that point where the catalyst is located, then you will see all these bursts appearing. Every burst in intensity corresponds to the formation of a single product molecule, followed by its diffusion out of the focal volume or by its photobleaching. Okay, so let's move on to the first example. We have studied alloperoxidase reactions. And we studied in particular two types of catalysts, being a bromoperoxidase enzyme, it's a naturally occurring enzyme, but we also studied its inorganic biomimic, and that's a tungstate exchange layered double hydroxide crystal. So this crystal has similar catalytic properties as the bromoperoxidase enzyme. What do these catalysts do? Well, from hydrogen peroxide and bromide salts, they generate very reactive hypobromide. This happens in a catalyzed primary reaction. And then in a secondary reaction, this reactive hypobromide can react with various organic molecules. And in our study, we used aminophenylfluorescein as a probe in this secondary reaction. This aminophenylfluorescein itself is not fluorescent, but upon reaction with hypobromide, it is converted into the strongly fluorescent fluorescein molecule. So with our fluorescence microscope, we can selectively look at the secondary reaction. So we can selectively look at the formation of these fluorescein molecules by hypobromide. Now, the key question here is, where does the secondary reaction take place? Because nowadays there is quite some debate in literature about this issue. And I will not go into too much details, but there are two hypotheses. There are people that say that hypobromide always is released from the catalyst, freely diffuses in the bulk solution, and performs a secondary reaction there. While there are reasons to believe that in some cases the hypobromide remains bound to the catalyst. And that there is, for instance, in the enzyme, a secondary binding place where the secondary reaction also proceeds in a catalyzed way. So we want to localize with high accuracy where this reaction is taking place, the secondary reaction. Okay, so here are some results of this measurement. So we immobilized the catalyst, the enzyme, and the LDH crystal on our cover slip in the microscope. We applied the reactants, the solution with the reactants. We focused on this catalyst, and here you see two intensity time traces from these catalysts. The upper one corresponds to a single enzyme, and the lower one to a single LDH particle. So indeed here you see this very low background level of fluorescence on which very intense bursts of intensities are superimposed. And every burst here corresponds to one individual reaction event of this secondary reaction. So actually this is quite amazing. We can really see at which time one individual reaction is taking place there. Okay, as I said, we want to know where this reaction is mainly taking place. So we didn't only focus on the catalyst itself, but we moved the laser focus at various or at increasing distances with respect to the catalyst. At every position, we recorded an intensity time trace with all these bursts, and we counted the amount of bursts happening as a unit of time for each position. And like this, we can construct the reaction profile, the spatial reaction profile for these catalysts. Now here are the results of that. So the reaction frequency of the secondary reaction is plotted here as a function of the distance from the catalyst. In blue you see the results for the LDH crystal, in black you see the results for the enzyme. And indeed you see that outside, when you focus outside or at a certain distance from the catalyst, you still see considerable amount of reaction events happening. It's like you have a constant level of reactivity until the reactivity drops to zero if you increase the distance further on. So this means that hypobromide is indeed released from the catalyst, and it's doing its action in the close surrounding of the catalyst, but not in or on the catalyst itself. So it's released, it travels a certain distance, in this case up to 1 micrometer away from the catalyst, and there it performs freely in the bulk solution its oxidation. So this means that hypobromide is kind of a vehicle transporting a reactive oxygen species that is generated from the mild oxidant hydrogen peroxide into the bulk solution, and there it can oxidize to more bulky substrates which normally, for instance, cannot or would not be able to reach the active sites of the catalyst because they're too big. So to conclude this first part, we could observe individual reaction events with hypobromide in two types of catalysts, biocatalyst and endogenous catalyst. And we could construct the distance profiles of the fluorescein formation, revealing that the secondary reaction takes place in the bulk solution, but close to the catalyst. So now let's move on to the second example. These are very recent results that we obtained on titanium MCM41 particles. These particles are mesoporous materials with a pore size of about 2.5 to 2.7 nanometers, and are known to have a good epoxidation activity and are used, for instance, to oxidize more bulky substrates that cannot enter, for instance, the micropores of TS1, which is also a good epoxidation catalyst. So, for instance, cholesterol can be used as a substrate, can be oxidized by hydroperoxides in titanium MCM41. And typically these particles from a typical synthesis procedure are a few micrometer in size. Now recently it was found that you can also make them in sizes of 100 or a few hundred nanometers. And it was found that these smaller particles have a much better efficiency for epoxidation. Now, one could not directly pinpoint the reason for this higher activity, but probably it is because there are some intraporous diffusion limitations in the large particles, meaning that only the outer part of the catalysts are really efficient, that the substrate cannot really reach the inner part. But there is no direct proof for this. Now, as I told that we can monitor single reaction events and localize them with fluorescence microscopy, this means that this is the ideal technique to investigate this hypothesis. So how do we do this in this case? Well, I told before that the key element in these experiments is the choice of a suitable fluorogenic probe. But in this case, we have a probe based on a body P dye. It's a very strong fluorescent dye. And we chose one that had butadiene bridge here. And because of this extended conjugation of the pi system, the color of the emission is quite red. Now, upon epoxidation, or if you add this to an oxidation catalyst, one of the two double bonds of the butadiene bridge will be selectively epoxidized, thereby breaking the conjugation, and what you get then is a blue shifted color of the emission. So we have a yellow emission, and thus by spectral selection we can selectively look at the formation of these atomic molecules. Now the size of this probe is between 1.7 and 1.8 nanometer along the long axis. This is similar to, for instance, cholesterol, which is a more commonly used substrate for this catalysis, meaning that it's a kind of representative substrate. It also means that it can really enter the pores. It's still much smaller than the nasal pores of the titanium MCM material. So we immobilized the titanium MCM particles on the cover slide, added the reactants and the probe. And here I will show you a movie of the fluorescence intensity that we could record from these experiments. I don't know if it's very clear, but you can see at the bottom part of this image vaguely the contours of three titanium MCM41 particles, here, here, and here. Each of them are a few micrometers in size. Now when I play the movie, I hope it works, you will see very short but intense flashes of light occurring every time a single epoxidation event is taking place. So you can already see that most of these flashes occur on the outer surface of these particles, but we want to localize them with high precision. So we want to do a more in-depth analysis of all these events. Actually, this is quite amazing. You can really directly see individual catalytic events, and you kind of light up all the active sites present there. Okay, so how did we analyze these images? So in principle, every flash of light has a certain width of about 250 nanometer in diameter because of the laws of diffraction. This is kind of the resolution that you have, but we want to go beyond this resolution. Now that's a nice thing when you look at single molecules. So you see the fluorescent spot from one single emitter, and because there are no other emitters in the neighborhood, it's well isolated, so you can really determine the center of mass of the emissive spot. And the center of mass of the emission corresponds to the exact location of your emitter. So by fitting this intensity profile, for instance, with the 2D Gaussian function, you can localize the emitter with an extremely high resolution down to the nanometer regime. Now, the accuracy depends on the signal-to-noise ratio, and the signal-to-noise ratio depends a bit from experiment to experiment and even between the different spots within one experiment. So for some spots, you can have really high down to nanometer resolutions, but what we can obtain in a really reproducible way is at least 15 nanometer resolution. So we're kind of trying to bridge the gap in resolution between normal optical microscopy and electron microscopy. We're not there yet, but we're trying to close the gap. Now, if you look at the results, so here I plotted, so in gray you see vaguely the contours of the titanium MCM41 particles. And on top of that, I plotted in red the fitted positions of all the flashes of light that we could see in an experiment during about 150 seconds. So every red dot is the accurately determined position of an individual turnover event, thus of an individual active site. Now you can indeed see that these dots are not very well dispersed throughout the whole particle, but mainly located at the outer rim of the particle. In the second example, you see some spots inside the particle, but probably this is because this is more like an aggregate of three particles here. Now, if you would zoom in on these regions, we can measure the distance over which turnovers are taking place, and this is typically a few hundred nanometers. So this means that only the outer titanium sites are efficiently used in the catalysis. And this really confirms the hypothesis that intraporous diffusion limitations are the limiting factor here in the catalysis. So before the probe can reach the inner part of the particle, it is already converted by the active sites. Now, one of the critics we sometimes get on this work is that we cannot stir in our reaction present. Because if we would stir it, the particles would no longer be immobilized and analysis would be very difficult. So this means that we might face problems of substrate depletion from the bulk solution towards the particle. But we can calculate the degree of substrate depletion because we know the bulk concentration of the probe. We know the activity of the particles, that's what we measure, and we can estimate the diffusion coefficient of the probe. So in principle, we have all the parameters to calculate the concentration gradient from the bulk towards the particle. And in our case here, this is only a few nanomolar, while the bulk concentration is half a micromolar. So we can exclude that the fact that we do not stir really influences the rate of the reaction that we see. Another thing that we checked is that there is no titanium gradient in the particle. We only see reaction at the outer rim of the particle. This might mean that there's only titanium present at the outer rim, but that's not the case because we performed XPS measurements to determine the surface concentration of titanium, and this was in good agreement with the bulk titanium concentration that we measured from chemical elemental analysis. There's also no pore blocking, so in principle the probe would be able to reach the inner volume of the particles. This we confirmed by doing actually the same experiment, adding the fluorescent probe to the particles, but in the absence of the oxidant. And if you apply excessive substrate, then you really see that also the inner parts of the catalyst become fluorescent. So to conclude the second example, we could directly visualize diffusion limitations in heterogeneous catalysis, and we could measure the length scales over which these limitations are taking place. And this can be done with a resolution of at least 15 nanometer. We can obtain higher resolutions, but this is what we can get in a reproducible way. And this is thanks to the single molecules sensitivity. Now, other things we're doing with fluorescence microscopy related to catalysis is, for instance, the construction of pH profiles of individual enzymes. And we see that there, for instance, not every enzyme responds to the same extent to the addition of base, for instance. Every single enzyme from what is supposed to be a homogeneous batch has a different pH optimum and is more or less susceptible to pH decrease. Another thing that we're working on is the fluorescent properties of silver exchange zeolites. So things that we can do with our microscope is we can do laser-induced creation of fluorescent silver particles at the nanoscale inside the zeolite. And these particles might have interesting analytic properties, which we will also try to analyze in the future. Now, to conclude this talk, I would like all the people that are involved in this research, and of course I would also like to thank FW and IWD for financial support, and thank you for your kind attention.
Thanks for a very nice presentation. We have a couple of questions. Yes, please.
I'm actually curious if you calculated the turnover frequencies for your haloperoxidase experiments.
Yes, the question is if we could calculate the turnover frequencies for the haloperoxidase reactions. Well, it's in fact quite difficult because we are looking at the secondary reaction, which is not, so that the reaction frequencies that we obtain is not always directly related to the real turnover frequency. So it's not sure that every produced hypobromide molecule will also convert an APF probe molecule. The second reason why it's quite difficult is that it's just not all happening in or on the catalyst itself. It's happening in the neighborhood of the catalyst, making it more difficult for us to count all the reaction events. But we can kind of estimate it. We know, for instance, if we focus in a certain volume, we know the volume of that, and we can extrapolate it to the whole volume around the the catalyst. And like this we can estimate it, and then it is in line with what we obtain from load measurements, or what is reported in literature from load measurements.
Any other question? Oh, a good one. Can you change the environment of your reaction so that you can, say, eliminate diffusion or decrease it and observe with your technique? Like a flow, for example?
Yeah, you can work in a flow. It's not that easy, but at this moment we are doing some flow experiments, not on this system, but on other systems. But then you have to take care to immobilize your catalyst in a careful way in order not to let it go. So it's difficult, but it's possible. We can play to a certain extent also with the temperature, but it's not that easy. To a certain extent you can change the conditions.
Okay. Yeah. Well, thank you for staying. Thank you to our speaker, to our chair, and we've finished this session, and thank you again.
Okay, if you'll get seated, we'll be ready to start the session here in just a moment. Good afternoon. My name is Patrick Wells from Texas A&M University. My chair in the session. My co-chair today is Thomas Degnan from ExxonMobil, Research and Engineering. This afternoon we'll have a keynote lecture followed by 3 talks. Keynote lecture of length of 40 minutes, talks all of length 20 minutes with a break. Following that, and then we'll have 5 more talks. We hope at least, since we're still looking for a couple authors. If they don't show up, if someone wants to give us a lecture, you're welcome to come on up. We'd like to do that. Okay, I'm going to turn the floor over to my co-chair, and he will be introducing the first 2 speakers. Thank you.
Thank you very much, Patrick. For those of you on my right, you may want to move to the left. The speaker's going to, what worked this morning really well was to for the speaker to actually stand right over here and you point from that